Hello everyone. This video is about Chapter 11, Simple Linear Regression. Regression is widely used in the real world to find out relationship between different factors, such as for quality control, stock prediction, gene mapping, and demographic. In this chapter, I will use the house example to demonstrate the data analysis of regression. As we know, many factors will influence the price of a house, such as the area of the house, the lot size, the built year, the number of bedrooms, and number of bathrooms. Now, we will only consider only one factor, such as the area of the house, to find out how the area of the house influences the house value. Is it bigger house, more expensive, or bigger house, less expensive? That is the simple linear regression. So, simple linear regression is a one-to-one relationship. We will set up a mathematical model. We call y-dependent variable, such as the house price, which is depend on a variable x, which is called independent variable, such as the area of the house. So our aim is to find out the function. House price will equal to a function of the area, so that we can predict the house values based on the area in the future. To make the model more accurate, we allow error exist, which is called random error. Now, let's set up the mathematical model. Y equals beta 0 plus beta 1 times x plus epsilon. Well, y here is dependent variable or response variable. X here is independent or predictor variable. Epsilon is random error. Beta 0 is the y-intercept of the line, and beta 0 is the slope of the line. For the plot, it will look like a straight line for simple linear regression. In this plot, beta 1 is the slope. If beta 1 is positive, it will be an increased line. If beta 1 is negative, it will be a decreased line. Beta 0 is the y-intercept. Now, let's see how to fit the model. We will use the least square approach to fit the model. Here, we will make 4 assumptions of the random error. That is 1. Mean of 0. 2. Constant variance. 3. Independent. 4. Normally distributed. After we finish the data analysis, we need to check the assumptions. We will discuss this later. Because we have made the assumption that the mean is 0, we can take average of the equation. The average of the epsilon will be 0 then. The equation will be y bar, which is the average of all y's, equals to beta 0 plus beta 1 times x bar, which is the average of all x's. Y bar can also be denoted as EY. Here are the formulas for the least squares estimate, where SSXY and SSXX are shown as follows. Now we will use software Excel to do the data analysis. Please watch the other videos for the instructions of using Excel. Here, I will use a sample data of houses which are near our school. Y here is the house value, and X here is the area of the house, the square footage. We will use Excel to find the relationship. Here is the output result from Excel for the simple linear regression model. Firstly, we will look at the significant f, which is a p-value. We will learn more about p-value in Chapter 8. If the significant f is smaller than 0.05, the model is significant or important. Here, we use 0.05 as a significant level, which is the most common significant level. You can understand as how much error you allow for this model. Usually, we allow 5% error as the most common level, which is 0.05. In this output, you may notice that the significant f here is 2.26152 e negative 16, where e negative 16 is 10th negative 16th power, a very small number, smaller than 0.05. So, the model I set up is significant. Secondly, we look at the p-value. If the p-value is smaller than 0.05, the parameter is significant or important. We have two p-values here. The p-value for the intercept is 2.63729 e negative 10, smaller than 0.05. So the parameter of intercept is significant. Also, the p-value for area is 2.26152 e negative 16, also smaller than 0.05. So the parameter of area is also significant. Under the coefficient, this one is beta 0 estimate, y-intercept. And this one is beta 1 estimate, the slope. So the equation y equals to beta 0 plus beta 1 times x. From the output, the equation will be y equals 307953 plus 195 times x. In the future, given any house area, you can predict the value of the house using this model. Now, let's see more results from the output. Here, multiple R, the correlation or strength of linear relationship between x and y. The result is 0.913, which is close to 100%, and that means the relationship is strong. Another one is R squared. The amount of variation is explained by the model. That explains whether the model is a reliable predictor of Y. In this model, 83.3% of variation is explained, which is relatively high. So the model is relatively reliable. Usually, if it is higher than 50%, more than half of variation is explained, we can see it is relatively reliable. The next one is standard error of the regression. Remember, before we set up the model, we make 4 assumptions of the random error. We will use plots to check the 4 assumptions. For the first 3 assumptions, mean of 0, constant variance, and independent, from the output plot, residue plot. For the last assumption, normally distributed, we will use the output plot, normal probability plot to check. Let's check one by one. For the mean of 0 assumption, if the overall plot in the residue plot is symmetric to 0, it satisfies the assumption. Otherwise, it does not satisfy. For the constant variance assumption, if overall you can fit 2 parallel lines to 0 in the residue plot, it satisfies the assumption. Otherwise, it does not satisfy. For the independent assumption, if overall there is no pattern in the residue plot, it satisfies. Otherwise, it does not satisfy. For the last one, normally distributed assumption, we check the normal probability plot. If you can fit a straight line, it satisfies. Otherwise, it does not satisfy. Let's see the plot. Here, from the residue plot, it looks like that all the dots overall are not symmetric to 0, more on the top. So we can see it does not satisfy the assumption of mean of 0. Next, if you argue that you can fit 2 parallel lines to 0, it satisfies the assumption of constant variance. Or, if you argue that you can't fit 2 parallel lines to 0, it does not satisfy the assumption of constant variance. It depends on how you argue, which is a little bit subjective. Here, from the residue plot, it looks like there is no pattern. It does not look like anything, so it satisfies the assumption of independent. Lastly, we look at the normal probability plot. It looks like a curve more than a straight line, so it does not satisfy the normal probability assumption. Furthermore, if it does not satisfy the assumption for assumptions, we need to do more about the data, like take a log or exponential. That will be more advanced statistics class. That's all for this video.